These chocolate bars are not crafted by hand, but constructed through a carefully controlled industrial process built for speed and precision. Behind the scenes, flowing chocolate-layered fillings and calibrated molds work in perfect sequence to shape wafers, coconut, and nougat into distinct signature bars. In this video, we explore how Kinder Bueno, Bounty, and Baby Ruth are assembled on factory lines, revealing the systems that turn raw ingredients into iconic chocolate worldwide. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow-metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber, where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station, where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion, with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, the mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm, depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill-seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems. Salmon production begins immediately after harvesting with rapid transport of whole fish to processing facilities. The fish are received in chilled holding tanks or insulated containers with ice slurry, where temperature is maintained near 0 degrees Celsius to minimize enzymatic activity and microbial growth. Once unloaded, the fish are fed into a de-icing flume system, where circulating chilled water removes surface ice and any external debris. After de-icing, fish are conveyed by stainless steel belt or pneumatic water transport to the grading station. Grading machines use load cell equipped conveyor belts or camera-based systems to categorize each salmon by weight class and body dimensions. Size data is recorded and used to assign each fish to a specific processing line depending on target product specifications. Following grading, salmon are transferred to stunning and bleeding stations. Here, automated percussive or electrical stunning devices render the fish unconscious in under 1 second. Immediately after stunning, a rotary knife or fixed blade system incises the gill arch. The fish then enter a bleeding tank or conveyor where they are held for 5-10 minutes in chilled water to drain blood via circulatory pressure, improving flesh appearance and shelf life. Next is deheading and gutting, where fish are positioned by automated orientation systems to align uniformly before high-speed rotary blades remove the head. The carcasses pass through a ventral incision machine where circular or V blades open the abdominal cavity. Viscera are extracted using vacuum suction nozzles or mechanical scrapers. Internal membranes are further removed by pressurized water jets aimed at the peritoneal cavity. A water flusher system removes residual debris. Eviscerated salmon proceed to the trimming section, where trained operatives or automated vision-guided blades remove the kidney line, dorsal fin remnants, and any remaining membrane tissues. Machine-assisted trimming modules use camera detection and robotic knives for precision cuts at high speed. Visual scanners inspect the cavity for any leftover material. After trimming, fish are re-washed using chilled, potable water from multiple spray nozzles. Washed carcasses are fed into a filleting machine. This equipment uses belt-fed positioning and blade pairs to cut along the spine, separating the two fillets. These blades are height adjusted based on pre-scanned fish dimensions to ensure optimal yield. The resulting fillets are guided into discharge lanes, while frames and collars are diverted to co-product processing. Post-filleting, fillets move to a pin bone removal station. This step is performed using mechanical bone pullers with rotating rubber wheels and suction extraction. The system identifies bone position based on predefined muscle anatomy and removes intermuscular bones without damaging the surrounding flesh. Depending on line setup, bone removal can also be conducted manually with tweezers for premium products. Fillets then pass through trimming belts, where tail tips, belly flaps, collar edges, and skin tears are removed. Trimming can be configured based on customer specification. Camera-based sorting systems ensure uniformity, and deviations trigger diverters to reroute products for manual correction. The next stage is skin removal. Skinning machines feed fillets into a blade interface that separates the skin from muscle while minimizing meat loss. Blade pressure, feed rate, and depth of cut are adjusted via servo control systems. Some processing lines retain the skin for specific markets or product forms. After skinning, fillets are conveyed to portioning systems. Portioning is carried out with water jet cutters, ultrasonic blades, or mechanical slicers. Laser-guided mapping scans the fillet to define weight and shape. Cutting systems then divide the fillet into precise portions according to program parameters, such as fixed weight steaks, loins, or saku blocks. Cut portions are collected in synchronized lanes for immediate packing. In parallel, whole fillet lines bypass the portioning system. These fillets are passed through grading systems based on fat line visibility, color, and size. Multi-sensor units evaluate each fillet with color cameras, near-infrared sensors, and weight scales. Graded fillets are sorted into categories and routed accordingly. Chilling is applied before packaging. Fillets and portions are passed through a spiral or tunnel chiller where they are cooled with cold air or flaked ice mist to reduce core temperature to below 2 degrees Celsius. Chilling units use digital thermostats and humidity sensors to maintain consistent internal environment and airflow. Once chilled, the product enters the packaging zone. Here, fillets and portions are loaded into trays or vacuum pouches. Modified atmosphere packaging is commonly used, where oxygen is displaced and replaced with CO2 and N2 in precise ratios to extend shelf life. Gas mixtures are controlled by flow meters and validated with gas analyzers. Trays are sealed with lidding film using heat sealing units that ensure proper adhesion and headspace control. Vacuum packaged products are loaded into form-fill seal machines, which mold film around the product, evacuate air, and seal the pack in a continuous motion. Vacuum level, seal time, and film tension are PLC controlled. Pack integrity is tested using pressure decay sensors or inline leak detection systems. After packaging, units proceed to labeling and coding. Print and apply labelers affix product labels with weight, species, origin, and batch codes. Inkjet or laser coders apply best before dates and traceability codes on film or trays. Optical scanners verify label placement and print clarity. Packaged products are then grouped into secondary packaging units. Collating conveyors align packs for insertion into cartons or crates. Case packers load these into pre-formed boxes. Automated box sealers apply tape or glue to secure the cartons. Tertiary barcodes are printed for shipping and scanned for inventory integration. Sealed boxes are routed to palletizing cells. Robotic palletizers stack boxes according to predefined patterns using vacuum heads or fork grippers. Pallets are wrapped with stretch film and labeled with shipment data. Each pallet is scanned and assigned a warehouse location in the inventory management system. Cold chain is maintained throughout with temperature sensors on conveyors, in holding rooms, and inside chilling units. Deviations trigger alerts and system flags. Data is logged and linked to each batch for traceability. End product temperatures are sampled using calibrated probes to verify compliance. Co-product handling operates in parallel. Salmon heads, frames, belly trims, and skin are collected separately. Heads and frames are directed to fish meal or oil extraction. Trimmed bellies may be sorted for smoking or mincing. Skins are graded and can be air-dried or frozen for export. All co-products are processed using stainless steel conveyors, crushers, or mincers with washdown capability. Smoking lines, if present, begin with brining or dry salting. Fillets are conveyed to tumblers or brine tanks, where salt concentrations and immersion time are automated. After salting, fillets are dried in humidity-controlled rooms before entering the smokehouse. Smoke is generated from wood chips or liquid smoke atomizers. Parameters such as smoke density, temperature, and air velocity are digitally controlled. After smoking, fillets are cooled and sliced using parallel slicers calibrated for thickness. In freezing operations, portions or fillets are directed to spiral freezers or contact plate freezers. Products are loaded onto stainless steel belts that pass through cold chambers at -35°C to -45°C. Dwell time is adjusted for product thickness to reach core temperatures below -18°C. Frozen products are bagged and sealed before moving to cold storage. Steak production begins after the animal carcass is chilled post-slaughter. Carcasses are held in cold storage rooms at 0°C to 2°C for 24 to 48 hours to complete rigor mortis and stabilize muscle structure. After this phase, the chilled sides are moved to the fabrication area using overhead rail systems equipped with trolleys. The first step is primal cutting. Sides of beef are placed on breaking tables and cut into primal sections using bandsaws and large breaking knives. The carcass is separated into forequarter and hindquarter at the 12th and 13th rib. The forequarter includes the chuck, brisket, rib, and plate, while the hindquarter contains the loin, round, and flank. From the hindquarter, the loin primal is isolated, which contains the strip loin, tenderloin, and short loin, common sources for high-grade steak cuts. The rib primal from the forequarter contains the ribeye section. Each primal is weighed, tagged with traceability information, and placed into designated bins or hooks. Primal sections are then moved to the boning line. Here, trained operators or automated knife systems remove bone structures. For ribeye and strip loin, the chine bone, feather bones, and spinal processes are removed using powered wizard knives or mechanical boning blades. Tenderloins are peeled away from the lumbar region with membrane knives, preserving the natural shape and minimizing yield loss. After deboning, cuts proceed to surface trimming, where external fat, silver skin, and connective tissues are removed. Precision trimming is performed using hand tools or vision-guided trim robots. Final trim levels are determined by target specifications, such as 1 4-inch fat cap or lean trim. The trimmed subprimals are transferred to aging rooms or directly to portioning, depending on the program. If aged, subprimals are vacuum packed using thermoforming machines and stored under controlled conditions at 0 degrees Celsius to 2 degrees Celsius for wet aging. Typical wet aging periods range from 14 to 28 days, depending on product line. Aged subprimals are retrieved and conveyed to the portioning area, where they are unpacked and visually inspected. Excess purge is drained, and the product is patted dry if needed to ensure consistency during slicing. Subprimals are loaded onto scanning tables equipped with 3 D-laser or X-ray systems. These systems analyze dimensions, fat distribution, and muscle structure to optimize cutting paths. Based on scan data, subprimals are transferred to automated steak portioning machines. These use rotating circular blades or water jet cutters to slice steaks at consistent thickness and target weight. Blade systems are servo-controlled to adjust angle and pressure in real time, compensating for shape variability. Common cut configurations include ribeye steaks, strip steaks, T-bone, porterhouse, sirloin, filet mignon, and top blade flat iron. Each type is portioned according to thickness specifications, typically ranging from 12 mm to 38 mm, and target weight tolerances within +1%. Cutting yield and number of steaks per subprimal are calculated live by onboard processors. Each steak is then conveyed to a weighing and grading station. Individual steaks pass over in-motion scales to confirm net weight. High-resolution imaging systems evaluate marbling score, surface integrity, and lean color. Grading software assigns visual quality rankings, and steaks are automatically sorted into output lanes based on specification match. Steaks requiring tenderization are routed through mechanical tenderizing machines. These consist of rotating blade rollers that pierce the muscle to sever connective fibers without altering surface appearance. For certain cuts like top round or sirloin, multiple passes may be used to reach the desired tenderness level. At this stage, enhancement or marination systems can be applied. For value-added products, steaks are loaded into vacuum tumblers or injector systems. Vacuum tumblers rotate the meat with liquid solution containing water, phosphate, salt, and flavoring. Injectors use multi-needle heads to evenly distribute brine through muscle fibers at defined pickup rates. Enhanced steaks are rested in staging bins for a defined soak period, then reweighed to verify target pickup has been achieved. Stricter control is maintained for fixed weight packs, where brine gain must fall within narrow tolerances to avoid over or under packaging. From here, steaks are conveyed into the packaging line. For fresh retail presentation, steaks are placed into polystyrene trays with absorbent pads and conveyed under MAP systems. Trays enter a sealing unit where oxygen is displaced with gas mixtures and overwrapped with clear lidding film. For vacuum-sealed steaks, portions are transferred to form-fill-seal machines. In these systems, bottom web film is thermoformed into pockets, steaks are loaded manually or robotically, and top film is vacuum sealed over the product. Seal bars apply pressure and heat to ensure consistent seal quality. Vacuum sealed steaks, intended for frozen distribution, are routed immediately to spiral or plate freezers. Steaks are individually frozen to core temperatures below 18 degrees Celsius in 30-60 minutes, depending on thickness. Frozen steaks are then bagged or boxed in bulk, with barcode labels applied for inventory tracking. Finished packs pass through metal detection and weight verification systems. Inline metal detectors scan for stainless, ferrous, or non-ferrous contaminants, rejecting non-conforming packs. Check weighers confirm that net weight falls within compliance range. Data is logged to the MES system and linked to batch production ID. Packs are labeled with product name, weight, grade, origin, and expiry using thermal inkjet printers or automatic label applicators. Optical sensors ensure correct label application, alignment, and data accuracy. Invalid or missing labels trigger rejection and pack removal. Labeled steaks are grouped using robotic case packing systems. Retail packs are placed in corrugated shippers or RPCs, arranged according to order profiles. Case formers and glue applicators prepare cartons, which are sealed and labeled with GTIN, lot, and dispatch codes. Cases are moved to palletizing stations, where robotic arms stack them into predefined patterns on wood or plastic pallets. Pallets are then wrapped in stretch film for load stability and scanned into inventory management systems. Each pallet is assigned a location in chilled or frozen storage, depending on product type. All processing zones are monitored with environmental sensors. Temperature, humidity, and air velocity are logged continuously. Conveyor speeds, blade RPMs, cut counts, and yield rates are tracked via PLCs connected to a central SCADA system. Downtime, throughput, and machine error logs are accessible in real time. Quality assurance procedures include destructive sampling and analytical testing. Random steaks are removed and evaluated for marbling score, thickness, weight accuracy, pH, water holding capacity, and sensory characteristics. Steaks are cooked under controlled conditions to assess texture, flavor, uniformity, and juiciness. Chicken strip production begins with the reception of chilled, deboned chicken meat, typically composed of boneless breast fillets. These are transported in bulk containers from upstream slaughter and deboning facilities. On arrival, the meat is inspected for temperature compliance, then tipped into stainless steel hoppers for transfer into the cutting line. Chicken fillets are conveyed to the portioning section, where they are aligned on belts and scanned by high-resolution cameras coupled with laser or X-ray systems. These scanners detect size, shape, and internal structure. Data is processed in real time to guide water jet or blade-based cutters that slice each fillet into uniform strips based on predefined weight, length, and thickness tolerances. Strips are conveyed into a trimming and inspection zone. Here, off-spec pieces, connective tissue, and surface fat are removed by automated blade systems or manually trimmed depending on the processing setup. A secondary vision system performs quality control on the stripped portions, ejecting defective pieces using pneumatic nozzles. Trimmed strips move into the marination system. The marination line consists of tumbling drums or vacuum massagers. Strips are loaded into the drum, which rotates while marination solution is injected or poured in. Marinade is typically a blend of water, salt, phosphates, modified starches, and flavor compounds. Ingredient mixing tanks feed the drum with chilled solution via peristaltic or centrifugal pumps. Drums operate under partial vacuum or atmospheric pressure depending on marination type. Vacuum assists protein extraction and enhances moisture retention. Tumbling speed and duration are controlled digitally, typically operating at 612 revolutions per minute for 15, 25 minutes. Finished marinated strips are discharged onto dewatering belts to remove excess surface marinade. Moisture-adjusted strips are conveyed into the coating system, a multi-stage line that applies a breading or batter system to each piece. The first stage involves pre-dusting, where strips are evenly coated with dry flour or modified starch powder to improve batter adhesion. Pre-dusting is applied via vibratory sifters and curtain feeders with excess powder removed by air blowers. Coated strips proceed to the battering station, where they pass through a liquid bath consisting of water, wheat flour, leavening agents, gums, and spices. Batter is recirculated continuously through inline filtration and agitation systems to maintain uniform viscosity. Strips are submerged using conveyor paddles, then raised through a vibrating belt to allow excess batter to drip off. Next is the breading application. Strips are dropped into a bed of dry breading mix, which may consist of breadcrumbs, cornmeal, or tempura crumbs. Top and bottom conveyors press breading into the meat surface. Breaders feature reflow systems that recirculate unused coating material after sifting out fines. Compressed air jets remove excess coating. For products requiring double coating, the batter and breading stages are repeated with a secondary set of machines, typically using coarser crumb materials for texture variation. Each station is monitored for line speed, dwell time, batter pickup, and breading adhesion. Strips then enter a setting fryer or pre-fry system. The setting fryer contains oil heated to 180-200 degrees Celsius and is typically 10-30 seconds in duration. This step partially cooks the outer coating to fix structure and prevent loss during freezing. Fryer oil is continuously filtered and circulated to maintain clarity. Exit temperature and surface moisture are measured in line. Post-fry, strips are transferred to a cooling conveyor that uses forced ambient or chilled air to reduce product temperature to under 30 degrees Celsius. Cooling prevents condensation in the next stage and prepares the surface for freezing. Conveyors are made of mesh belts for air penetration. Air velocity and temperature are controlled to stabilize product dimensions. Cooled strips are arranged in rows and conveyed into the freezing tunnel. Spiral or linear IQF freezers are used. Inside the tunnel, product is exposed to high velocity air at temperatures between 35 degrees Celsius and 45 degrees Celsius. Belt speed and airflow are calibrated to bring the product core temperature below 18 degrees Celsius within 15-25 minutes. IQF technology ensures each strip remains separate by using belt vibration, cryogenic burst, or pre-chill alignment. Ice accumulation and belt defrosting are controlled via automated heat pulse cycles. Tunnel freezers are cleaned in place and monitored for temperature uniformity. Once frozen, strips enter the weighing and sorting station. Multi-head weighers mounted above packaging lines portion strips into programmed weight ranges. Optical or X-ray systems recheck for foreign materials, bone fragments, or density anomalies. Rejected product is diverted automatically. Weighed portions drop into bags or trays using form-fill seal equipment. For pillow bags, film is pulled from rolls, formed into a tube, filled with product, and sealed at the top and bottom by heated jaws. For tray packs, plastic trays are filled and lidded with sealed film using MAP systems, replacing ambient air with nitrogen and carbon dioxide. Each pack is labeled with product ID, batch number, and expiration using inkjet printers or label applicators. Vision systems confirm label placement and code legibility. Weighed packs are verified for target range and conveyed to check weighers. Under or overweight packs are removed via pneumatic rejectors. Packaged units are collated and loaded into cartons. Carton erectors fold and glue cases while robotic arms load a fixed number of bags or trays per box. Cartons are sealed, labeled, and scanned for tracking codes. Logistics data is applied using print and apply labelers that communicate with the plant's ERP system. Boxes are transferred to robotic or gantry-style palletizers. These systems stack cases on wooden or plastic pallets in staggered patterns to optimize height and weight distribution. Pallets are stretch wrapped using rotary arm or turntable wrappers. Finished pallets are tagged with shipment barcodes and stored in cold storage warehouses maintained at 20 degrees Celsius. All processing stages are monitored by a PLC integrated SCADA system. Control points include marination pump flow, batter viscosity, breading density, fryer oil temperature, freezer airspeed, and packaging line synchronization. Recipe management software ensures every batch conforms to target formulation and processing times. Sensor data is collected from load cells, thermocouples, optical sensors, belt encoders, and pressure gauges. Line operators access live performance dashboards from HMIs to monitor throughput, reject rates, and downtime per station. Alarms and parameter deviations are logged in the plant MES. Quality assurance involves sample testing at key stages. Strip dimensions are measured post-cutting with digital calipers. Batter pickup percentage is calculated by weight differential before and after coating. Oil content is checked using Soxhlet extraction post-fry. Internal temperature is verified post-freeze using calibrated thermometers. Microbial samples are taken from finished product and contact surfaces. Swabs are tested for total plate count, Listeria SPPER, and Salmonella SPP. Moisture, protein, and fat levels are confirmed via NIR spectroscopy or gravimetric methods. Product consistency is tracked against batch specifications. Yield data is compiled for raw input versus packaged output to monitor efficiency. Trimming loss, batter loss, breading recycle rates, and oil usage per kilogram of product are calculated for cost optimization. Rework loops return trimmings and off-spec strips to reprocessing lanes if permitted. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees C to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in two stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300–500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60–80 degrees Celsius, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees Celsius to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50–55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 C, 160 C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase for the final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system, a stainless steel planetary mixer, or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low-shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps, monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high-shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture, invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree brix, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired brix and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed inline or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 degrees. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Labeled jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. Pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability. Toothpaste production begins with the batching of raw materials into 3 primary categories: abrasives, humectants, and active ingredients. These components are stored in bulk silos, intermediate bulk containers, and stainless steel drums positioned adjacent to the central mixing facility. Ingredient delivery is managed through automated vacuum conveyors, liquid transfer pumps, and weigh-scale monitored feeders. Abrasives are typically calcium carbonate, hydrated silica, or dicalcium phosphate dihydrate. These powders are conveyed through enclosed pipelines and loaded into high-shear mixing vessels fitted with load cells. Particle size of abrasives is controlled within 5 to 15 microns for optimal cleaning performance without excessive enamel wear. The feed rate is calibrated by rotary valve controllers. Humectants, primarily sorbitol solution, glycerin, and propylene glycol, are stored in temperature-controlled, jacketed tanks. These are pumped into the mixer through flow meter regulated dosing lines. The purpose of humectants is to retain moisture, maintain paste consistency, and prevent drying inside the tube. Viscosity and density of each liquid are tracked by inline sensors during transfer. Deionized water is introduced in precise volume based on formulation requirements. The water is pre-treated via reverse osmosis filtration and UV sterilization, then dosed into the batch using mass flow controllers to ensure accurate hydration of solids. Active ingredients such as sodium fluoride or stannous fluoride are pre-blended in secondary mixing tanks before being introduced to the main mixer. These compounds are sensitive to pH and temperature, requiring separate handling. Dosing is performed using positive displacement pumps to achieve concentrations typically around 0.24% for fluoride ion. A surfactant, usually sodium lauryl sulfate, is added last due to its foaming and emulsifying properties. It is introduced in liquid or paste form through heated lines maintained at 30 and 35 degrees Celsius to reduce viscosity. SLS is blended gently to avoid excessive aeration. The target inclusion level ranges between 1.0 to 2.0% depending on the formulation. Hydrocolloid binders such as carboxymethyl cellulose, xanthan gum, or carrageenan are pre-dispersed in warm water before being added to the mixture. These agents control rheology and prevent phase separation. Dispersion tanks use overhead agitators operating at low RPM to avoid clumping. Hydration time is monitored to ensure full polymer expansion before integration. Flavoring oils like spearmint or peppermint are stored in sealed drums and introduced through small volume dosing systems equipped with peristaltic pumps. Flavors are highly concentrated and dosed between 0.3–0.7% by weight. The addition is carried out under vacuum to prevent volatilization. Colorants such as titanium dioxide or FD&C dyes are added as aqueous slurries or predispersed concentrates. These are introduced late in the mix cycle for visual uniformity. Color matching is performed using spectrophotometric sensors positioned above the mixing vessel. Once all materials are loaded, the main batch undergoes high shear mixing. The vessel uses multi-stage impellers, typically a bottom-mounted anchor blade for macro movement and a rotor-stator head for localized dispersion. Mix time ranges from 30 to 45 minutes. Viscosity is continuously measured via in-tank torque sensors and correlated to predefined set points. The entire vessel is held under partial vacuum to remove entrained air. A vacuum pump system pulls air through condensers and liquid traps. Vacuum mixing prevents bubble formation, ensures uniform density, and improves the shelf stability of the final product. Once the batch reaches target viscosity and homogeneity, a recirculation loop begins. The mixture is pumped through inline homogenizers or colloid mills to further reduce particle size and eliminate agglomerates. Homogenization shear rates exceed 10,000 S1, providing a consistent microstructure. The homogenized toothpaste is filtered through stainless steel mesh screens, typically 80 to 120 mesh size, to remove any foreign particles or unblended residue. The product is discharged into vacuum holding tanks equipped with slow-speed agitators to maintain consistency while awaiting packaging. The filling process begins with the transport of toothpaste from holding tanks to the filling line through sanitary diaphragm pumps and flexible hoses. The product is kept under continuous agitation to prevent settling of heavier components. Tubes, either laminate aluminum or co-extruded plastic, are loaded into an orienting magazine. Tubes are fed one by one into indexing star wheels that position each unit beneath the filling nozzle. Optical sensors ensure correct alignment based on pre-printed registration marks. Filling nozzles are submerged slightly into each tube and retract upward during discharge to prevent air pockets. Volumetric filling pumps dispense the product in quantities typically ranging from 75 ml to 150 ml. Fill weight is controlled to plus 1% using servo-driven piston pumps or mass flow metering systems. Immediately after filling, the tube passes to the sealing station. For laminate or plastic tubes, the tail is heat sealed using conduction or impulse sealers. The sealing bars clamp the tube end, applying pressure and heat to fuse the inner layers. For aluminum tubes, the tail is folded and crimped mechanically by a multi-head crimping tool. A batch code and timestamp are embossed or inkjet printed onto the sealed end. This information includes production line, time, and lot number for traceability. The print heads are aligned with the tube transport belt and are capable of printing at over 300 units per minute. Filled tubes are ejected onto a conveyor and enter a carton loading station. Flat-folded cartons are erected using vacuum grippers and mechanical pushers, then held open under guide rails. Each tube is inserted automatically, and informational leaflets are added if required by formulation. Cartons are closed using hot melt glue applicators or tuck-in flaps depending on design. Sensors verify the presence of a tube inside each carton. Incomplete units are automatically rejected through diverter arms. Cartons are grouped into shipping cases via a robotic case packer. Cases are assembled from flat blanks, filled, and sealed using hot glue or tape. Case labels are printed and applied using print and apply applicators with real-time data from the production control system. Completed cases are moved onto a palletizer conveyor. An articulated arm robot stacks cases onto pallets in a predefined pattern. Slip sheets are inserted automatically, between layers to maintain stability. Full pallets are stretch-wrapped using rotating ring or arm wrappers. The film tension and overlap are adjustable to prevent compression of cartons while ensuring unit load integrity. Pallets are labeled on two sides with shipping and tracking information. Barcode scanners verify label accuracy and update inventory systems. Pallets are then transferred to staging zones for warehousing or direct shipment. During production, the entire process is governed by a centralized control system. Each piece of equipment is connected through a SCADA network, allowing operators to monitor tank levels, batch status, mix parameters, and fill rates from an HMI panel. Ingredient weighing stations utilize barcode scanners and recipe control software to prevent cross-contamination and ensure formula compliance. Any deviation from programmed weight tolerances triggers an alarm and locks further processing. Rheological properties are tested in real time using rotational viscometers. Samples from each batch are drawn via sampling ports and analyzed for yield stress, viscosity at shear, and thixotropy to confirm product performance. pH levels are measured with inline electrodes during mixing, typically targeting a range of 6.5 to 7.5, depending on the actives used. Fluoride ion concentration is verified using ion-selective electrodes to confirm dosing accuracy. Toothpaste density is measured using vibrating tube densitometers and compared against target values to ensure proper tube filling weight. Deviations are corrected by adjusting water content or mixing parameters. Color uniformity is monitored using inline spectrophotometers calibrated to CIE lab. Color space standards. Any deviation beyond preset delta E values prompts batch correction or rejection. Each major tank and mixer is equipped with CIP systems consisting of rotating spray balls, detergent feed lines, and automated rinse cycles. CIP cycles are logged in the MES to maintain batch integrity. Final packaging lines are equipped with vision systems to detect carton defects, misalignment, or barcode errors. These systems use high-resolution cameras and rejection logic to divert non-conforming packages. High-speed toothpaste production lines are capable of producing over 300 tubes per minute, with batch sizes ranging from 1,000 to 6,000 liters depending on demand. Formulation changes are executed by software-driven recipe management with automated valve sequencing and ingredient routing. Mouthwash production begins with the preparation of purified water, which serves as the base solvent for all ingredients. The water undergoes reverse osmosis, filtration, followed by ultraviolet sterilization. Conductivity meters and microbial sensors ensure that the water meets pharmaceutical grade specifications before being stored in stainless steel holding tanks equipped with continuous recirculation systems to prevent stagnation. Batch production starts with loading water into a stainless steel jacketed mixing vessel fitted with high shear agitators. The vessel is mounted on load cells to allow for precise weight-based dosing of each component. All ingredients are added in a controlled sequence based on formulation parameters pre-programmed into the batch control system. Humectants are added first. Glycerin, sorbitol solution, or propylene glycol is pumped from storage tanks using metered diaphragm pumps. Flow meters and temperature sensors track each transfer. These compounds help retain moisture and provide viscosity and sweetness. Typical inclusion ranges from 5 to 25% by weight. Alcohol, when used as a solvent and preservative, is added next. Ethanol is transferred from explosion-proof storage tanks through stainless steel piping. The addition is performed under closed-loop nitrogen-blanketed conditions to minimize evaporation. Flow rate is monitored by mass flow meters, and volume is logged digitally for each batch. Final ethanol concentration typically ranges from 15 to 27% in alcohol-based formulations. Active ingredients are added once the base solution stabilizes. These include antimicrobial agents, such as cetylpyridinium chloride, chlorhexidine gluconate, or essential oil blends. Active ingredient dosing is highly precise and performed using peristaltic pumps from sealed ingredient totes. Target concentration is verified using inline UV absorbance detectors or conductivity probes depending on the compound. Fluoride compounds, such as sodium fluoride or stannous fluoride, are prepared as pre-dissolved concentrates in separate mixing tanks using deionized water. These are dosed into the main batch at levels typically ranging from 225 to 1000 ppm fluoride ion. Addition is done slowly to avoid precipitation, and pH is adjusted immediately. Afterward, to maintain stability. Flavoring agents are next. These include mint oils, cinnamon, or eucalyptus derivatives. Essential oils are highly volatile and introduced using closed-loop pumps with nitrogen pressurization. Solubility is aided by pre-mixing oils with non-ionic surfactants or alcohol carriers before addition. Colorants are added in the form of water-soluble dye solutions or color dispersions. Each colorant is pre-weighed and diluted before dosing. Magnetic stirrers or inline static mixers ensure uniform dispersion. Optical sensors may be mounted over the mixing tank to confirm target lab or chess color values in real time. Preservatives such as methylparaben, propylparaben, or sodium benzoate are added next. These are introduced as aqueous solutions prepared in separate blend tanks. Preservative concentration ranges from 0.05–0.2% depending on product shelf life requirements and microbial load assessments. Addition is carried out under agitation to ensure full dissolution. Sweeteners such as sodium saccharin, xylitol, or sucralose are added to enhance palatability. These are dosed in small concentrations, typically below 0.5%, using high-precision auger feeders or micro-piston pumps depending on the form. Mixing continues at low speed to prevent foaming. The final mouthwash formulation is adjusted for pH. Aqueous solutions of sodium hydroxide or citric acid are prepared in auxiliary tanks and dosed using digital peristaltic pumps. pH is continuously monitored by inline probes to maintain a range typically between 4.5 and 7.0, depending on the active ingredients and flavor profile. Anti-foaming agents are optionally added during the final mixing phase. These include dimethicone emulsions or food-grade silicone oils. Addition is controlled via gear pumps and only applied when foaming exceeds threshold levels, as detected by capacitive foam sensors inside the vessel. After full ingredient incorporation, the batch is subjected to a recirculation loop using a centrifugal pump system. The liquid is passed through an inline homogenizer or static mixer to eliminate stratification and achieve consistent texture and solute distribution. The blended product is filtered through sanitary-grade filtration systems, typically consisting of 5 to 10 micron nominal filters followed by 0.45 micron absolute membrane filters. Filters are housed in stainless steel vessels with differential pressure gauges to monitor clogging. Filtration removes undissolved solids and potential contaminants prior to packaging. Filtered mouthwash is then transferred via sanitary pipelines to intermediate storage tanks or directly to the filling line. Holding tanks are jacketed and equipped with low shear agitators to maintain homogeneity. Each tank includes a vented filter to preserve sterility and pressure balance. Bottling begins with automatic bottle unscramblers that orient and feed empty bottles onto the production conveyor. Bottles are conveyed under a rinsing station where filtered air or ozonated water is sprayed into each bottle via nozzle inserts. Rinse nozzles retract after each cycle, and residual rinse is removed using vacuum-assisted drainage. Clean bottles move to the filling carousel. Volumetric or flow meter-based filling systems dispense liquid into each bottle. Nozzles are equipped with anti-drip valves and may dive into the bottleneck to minimize turbulence. Fill volumes are controlled to within +1 ml using servo-controlled pistons or mass flow controllers. Line speeds may exceed 200 bottles per minute, depending on bottle size and product viscosity. Filled bottles proceed to the capping station. Caps are sorted via a centrifugal feeder or vibratory bowl and oriented into a chute. A pick-and-place system applies each cap to a bottle, and servo-torque heads tighten the cap to precise specifications. Torque monitoring systems verify seal integrity for each unit. Induction foil sealing may be used, especially for alcohol-based or high-value formulas. Bottles pass under an induction coil, which heats the foil liner inside the cap. The foil bonds to the bottle, rim through localized heat and pressure, creating a tamper-evident, leak-proof seal. Labeled bottles proceed through a pressure-sensitive labeling station. Label spools feed through optical sensors and tensioning arms. Each label is applied to the bottle using rubber rollers or air jets and wrapped around the circumference. Vision systems verify label placement, orientation, and print quality. Optional shrink bands are applied for tamper evidence. Bands are dropped onto the bottlenecks and conveyed through a shrink tunnel heated by steam or infrared elements. Temperature control ensures uniform band shrinkage without damaging the label. Coded printing is applied next. Thermal inkjet or laser printers mark each bottle with batch number, timestamp, and expiration date. Printers are mounted on adjustable arms and synchronized with the conveyor motion to maintain legibility at high speeds. Bottles are collected into groups using pack-off tables or automated grouping conveyors. Depending on the packaging format, grouped bottles are transferred to a cartoner or case packer. Cartons are erected automatically, and bottles are inserted using push arms or robotic arms. Cases are formed using automatic case erectors. Cartons are loaded into corrugated shipping cases in a pre-programmed layout. Flaps are closed using hot melt glue or tape, and cases are labeled with shipping information using print and apply labelers. Completed cases are transported to palletizing systems. Robotic palletizers stack cases layer by layer using vacuum grippers or mechanical forks. Slip sheets are inserted as needed. Stack configurations follow warehouse layout and transport requirements. Each pallet is stretch wrapped using rotary arm or turntable systems. Stretch film is applied with controlled tension and overlap to stabilize the load. Barcode labels are applied to two adjacent sides for warehouse scanning. Throughout the entire production process, data is logged by a centralized manufacturing execution system. Ingredient usage, batch ID, tank temperatures, pH levels, fill weights, and cap torques are recorded in real time. Deviations outside of tolerance trigger automatic alarms and halt affected processes. Inline process analytical technologies are used for real-time monitoring of active concentration, color consistency, and microbial integrity. Ultraviolet spectrophotometers, or Raman probes, measure concentrations of key actives like fluoride or chlorhexidine without requiring sample removal. Inventory management systems track lot numbers of all raw materials and link them to finished product batches for traceability. Each component is barcoded and scanned before addition to a batch, ensuring compliance with formulation requirements. Shampoo production begins with the preparation of process, water, which functions as the primary carrier for all ingredients. Incoming water is treated through multi-stage filtration systems that include sand filtration, activated carbon beds, reverse osmosis membranes, and ultraviolet sterilization. Treated water is stored in stainless steel buffer tanks equipped with recirculation pumps to maintain uniform temperature and prevent stratification. The manufacturing process is typically batch-based, although some high-volume lines use semi-continuous systems. Each batch starts with charging a jacketed stainless steel mixing vessel with a calculated volume of purified water. The vessel is mounted on load cells that provide real-time mass data to the batch control system. Agitation begins immediately using a slow-speed anchor impeller to establish bulk circulation. Primary surfactants are added first. These are the main cleansing agents and usually include sodium lauryl sulfate, sodium lauryl sulfate, ammonium lauryl sulfate, or sodium cocoyl isethionate, depending on formulation. Liquid surfactants are pumped from storage tanks using variable speed, centrifugal, or positive displacement pumps. Flow is regulated by mass flow meters, and addition rates are synchronized with agitator speed to avoid excessive foaming. For formulations using solid or paste surfactants, the materials are pre-dissolved in auxiliary tanks. These tanks are heated via steam or hot water jackets to reduce viscosity and accelerate dissolution. High shear mixers are used to break down surfactant agglomerates before the solution is transferred into the main batch vessel. Once the primary surfactants are fully dispersed, secondary surfactants are introduced. These include cocamidopropyl betaine, sodium cocoamphoacetate, or other amphoteric surfactants that improve mildness and foam stability. These materials are dosed through metered pumps and blended under moderate agitation to ensure compatibility with the primary surfactant system. Thickeners are added next to control viscosity. Depending on the formulation, these may include sodium chloride, ammonium chloride, hydroxyethyl cellulose, xanthan gum, or acrylate-based polymers. Salt-based thickeners are dissolved directly into the batch using controlled dosing, while polymeric thickeners are prehydrated in separate dispersion tanks to prevent lump formation. Polymer dispersions are slowly added under high shear conditions to ensure uniform distribution. Conditioning agents are incorporated after viscosity begins to develop. These include cationic polymers, such as polyquaternium compounds, guar hydroxypropyl trimonium chloride, or silicone emulsions. Silicone conditioning agents, such as dimethicone or amidimethicone, are supplied as stable emulsions and added under low shear agitation to prevent emulsion breakage. The batch temperature is carefully controlled, typically between 30-45 degrees C, to maintain emulsion stability. Pearlizing agents are added when a pearlescent appearance is required. These materials often consist of ethylene glycol, distearate, or glycol monostearate dispersions. Pearlizing agents are melted in heated side vessels and added to the batch at elevated temperature. Controlled cooling is then used to crystallize the pearlescent particles, producing uniform light-reflecting platelets throughout the shampoo. Chelating agents such as disodium EDTA are introduced to bind metal ions present in water or raw materials. These are added early in the process, usually dissolved in water, to improve product stability and preservative effectiveness. Dosing is managed using precision pumps due to the low concentration required. Preservatives are added once the surfactant system is fully established. These may include phenoxyethanol, sodium benzoate, potassium sorbate, or blended preservative systems. Preservatives are typically added as liquid concentrates and dispersed thoroughly under continuous agitation. The concentration is controlled to achieve microbial stability without affecting product performance. pH adjustment follows. Shampoo formulations generally target a pH range between 4.5 and 6.5 to align with hair and scalp compatibility. pH adjusters, such as citric acid or sodium hydroxide, are prepared as dilute solutions in auxiliary tanks. These solutions are dosed gradually, while pH is monitored using inline probes connected to the batch control system. Adjustments are made incrementally to avoid overshooting target values. Fragrance is added near the end of the mixing process. Fragrance oils are complex blends of aromatic compounds and are typically pre-dissolved in a solubilizer or surfactant base before addition. This prevents separation or clouding. Fragrance addition is carried out under low agitation to minimize volatilization and foaming. Dosing is controlled with high-accuracy peristaltic pumps due to the low inclusion rate. Colorants are added as diluted solutions or dispersions. Liquid dyes are metered into the batch, while powdered pigments are pre-dispersed in water or surfactant solution to ensure uniform color distribution. Optical sensors or laboratory sampling is used to confirm color consistency against formulation standards. Once all ingredients are added, the batch undergoes a final homogenization phase. The shampoo is circulated through an inline rotostator mixer or colloid mill to eliminate micro lumps, improve clarity, and ensure uniform viscosity. Shear rates are carefully controlled to avoid degrading polymer thickeners or breaking silicone emulsions. During homogenization, air entrainment is minimized. Some systems apply vacuum to the mixing vessel to remove entrapped air bubbles. Vacuum levels are controlled to prevent excessive evaporation of volatile components such as fragrance. After homogenization, the shampoo is transferred to a finishing tank. This tank is equipped with gentle agitation to maintain homogeneity while allowing the product to cool to filling temperature. Cooling is achieved via the vessel jacket using chilled water or ambient cooling loops. Final viscosity develops during this cooling phase, particularly for salt or polymer thickened systems. Quality parameters are verified at this stage. Viscosity is measured using rotational viscometers, density is checked using digital densitometers, and pH is reconfirmed. Adjustments can still be made by adding small amounts of water, thickener, or pH modifier if required. The finished shampoo is then pumped through sanitary pipelines to the filling area. Transfer pumps are selected based on product viscosity and shear sensitivity, commonly using lobe pumps or progressive cavity pumps. Flow rates are synchronized with filling line demand to maintain steady supply. Packaging begins with bottle preparation. Empty bottles made from PET, HDPE, or PP are delivered to the line in bulk and fed into an unscrambler. The unscrambler orients bottles upright and transfers them onto a conveyor system. Bottles pass through an air rinsing station where filtered air removes dust or debris from the interior. Bottles are conveyed to the filling machine. Filling systems may be volumetric piston fillers, mass flow fillers, or time pressure fillers, depending on product viscosity and accuracy requirements. Filling nozzles descend into the bottleneck to reduce splashing and foaming. Fill volumes are controlled to tight tolerances, typically within plus 0.5%. Filled bottles move to the capping station. Caps are sorted and oriented using vibratory bowl feeders. Each cap is placed onto a bottle and tightened using torque-controlled capping heads. Torque values are monitored continuously to ensure consistent closure without deforming the bottle or cap threads. If induction sealing is used, bottles pass under an induction coil that heats a foil liner inside the cap. The liner bonds to the bottle rim, creating a hermetic seal. Coil power and conveyor speed are calibrated to ensure uniform sealing without overheating the product. Labeled bottles proceed to the labeling station. Labels may be pressure sensitive, shrink sleeve, or wraparound types. Pressure sensitive labels are applied using rollers and air jets, with registration controlled by optical sensors. Shrink sleeves are applied loosely and then passed through a heat tunnel where they conform tightly to the bottle shape. Batch codes and expiration dates are printed on the bottle or label using inkjet or laser coding systems. Print quality is verified by vision systems that detect missing or illegible codes and trigger rejection mechanisms. Bottles are then grouped for secondary packaging. Automatic packers collate bottles into predefined counts and load them into cartons or trays. Cartons are erected from flat blanks and sealed using hot melt adhesive. Case packers arrange cartons into shipping cases according to palletization requirements. Shipping cases are conveyed to palletizing systems. Robotic palletizers stack cases onto pallets in programmed patterns to maximize stability and space utilization. Slip sheets may be inserted between layers. Completed pallets are wrapped with stretch film to secure the load. Throughout the entire process, production is controlled by a centralized automation system. Programmable logic controllers manage ingredient dosing, mixing speeds, temperatures, and transfer operations. A supervisory control and data acquisition system provides real-time monitoring, data logging, and batch traceability. Recipe management software stores detailed formulation parameters, allowing rapid changeover between different shampoo variants such as moisturizing, clarifying, volumizing, or color protecting types. Automated valve manifolds route ingredients to the correct vessels based on the selected recipe. Raw material inventory is tracked digitally. Each ingredient lot is scanned and logged before use, and consumption data is automatically reconciled with production output. This ensures accurate material planning and batch traceability. Cleaning cycles between batches are executed using automated clean-in-place systems. These systems circulate cleaning solutions and rinse water through vessels, pipes, pumps, and fillers without disassembly. Cleaning parameters such as time, temperature, and flow rate are recorded for each cycle. Tim Hortons donut production begins with a dry mix formulation containing enriched wheat flour, sugar, dextrose, non-fat dry milk, salt, leavening agents like sodium acid pyrophosphate and baking soda, and dough conditioners. These dry ingredients are stored in silos or large bagged quantities and conveyed into industrial mixers via auger-fed hoppers. Water, maintained at a controlled temperature between 26-30 degrees C, is added automatically by volume through solenoid-controlled valves. The mixture undergoes a high-capacity mixing process using horizontal paddle mixers that operate for approximately 10 to 12 minutes until a smooth, elastic dough forms. Dough temperature is precisely maintained to ensure consistent gluten development. The mixed dough is transferred to a resting conveyor where it undergoes a short fermentation stage, typically lasting 10 to 15 minutes. During this period, gluten strands relax, allowing easier downstream sheeting and cutting. The dough enters a sheeting system composed of heavy-duty rollers that gradually flatten the dough to a uniform thickness, often between 8 to 12 millimeters depending on the donut type. A dusting system coats the sheet with a thin layer of flour or starch to prevent sticking. Next, rotary cutters mounted on a continuous belt use oscillating blades and die shapes to stamp out ring donuts, filled donut bases, and specialty shapes. Hole cutouts are collected via vacuum suction and reintroduced into the dough stream to reduce waste. The shaped pieces drop onto a mesh conveyor belt, which transfers them into a proofing chamber. The proofer is a humidity and temperature-controlled enclosure typically maintained at 38-42 C and 75-85% relative humidity. Here, yeast-leavened donuts undergo final fermentation for 35 to 50 minutes, doubling in size. Upon exiting the proofer, donuts enter a continuous fryer via an infeed belt that gently lowers each piece into the oil. The fryer is filled with high-stability vegetable shortening, held at a consistent temperature of 185-190 degrees C. Conveyor arms with paddles submerge the donuts briefly before flipping mechanisms rotate them halfway through the cycle to ensure even cooking on both sides. Each donut spends 90-120 seconds in the fryer. Oil filtration systems continuously circulate and clean the oil through mechanical filters and carbon filtration media to maintain clarity and extend oil life. Excess oil is removed from the surface by air knives as donuts exit the fryer. Fried donuts transfer to a cooling conveyor, where forced ambient air reduces product temperature before glazing or filling. For ring donuts, a waterfall-style glazing system coats the tops with sugar glaze. The glazing machine contains a recirculating pump that delivers a steady curtain of glaze to ensure uniform coverage. Filled varieties proceed to an injection station. A synchronized multi-nozzle injector aligns with each donut and dispenses a precise volume of filling, such as fruit jam, Bavarian cream, or chocolate, into the center of the pastry using piston-driven pumps. Fill volumes are regulated down to the gram for product consistency. Specialty donuts requiring additional coatings, such as powdered sugar or cinnamon sugar, enter a rotating tumbler. The tumbler's perforated drum allows excess sugar to fall through while evenly applying the coating as the donuts rotate inside. Sensors monitor rotation speed and coating application rate. For chocolate or icing-topped varieties, donuts pass through a curtain enrobing system or a top-down depositor. The enrobing system consists of a tempering kettle and a heated pump that maintains the chocolate or icing at its working viscosity, typically around 40-45 degrees Celsius. Topping depth is controlled by belt speed and curtain thickness. Donuts requiring sprinkles or toppings are conveyed beneath a waterfall depositor or rotary sprinkler. The toppings are dispensed from a vibrating hopper that ensures even spread. Static charge may be applied in some systems to increase topping adhesion to the wet icing. Once decorated or filled, donuts proceed through a spiral cooling tower. The spiral conveyor allows a compact vertical footprint while offering extended cooling time, typically 15 to 20 minutes. Forced air circulation removes residual heat, allowing products to stabilize before packaging. Each donut then moves through a vision-based quality control system. High-speed cameras scan for defects in size, color, fill placement, or topping consistency. Items outside. Tolerants are rejected automatically using pneumatic pushers. Qualified donuts are then grouped by variety and type using a servo-controlled collation system. Products are aligned into lanes and counted by photoelectric sensors, preparing them for packaging. Packaging is handled by an automated tray loading system. Flat-folded paperboard trays are erected using mechanical arms, and donuts are placed inside via pick-and-place robots with suction grippers. For assorted packs, robotic arms select donuts by type from buffer conveyors. Trays proceed to a lid applicator station, where pre-folded lids are pressed and sealed using glue jets or heat-sensitive adhesives. For retail cases, sealed trays are grouped and shrink-wrapped using polyolefin film, which is cut, wrapped, and heat-shrunk in a tunnel oven operating at around 160 degrees Celsius. Each finished pack receives an inkjet-printed date code and batch number from a variable data printer. The printer adjusts to the motion of the conveyor, ensuring clear marking without interrupting product flow. Packaged products are conveyed to palletizing stations. Robotic palletizers equipped with vacuum or mechanical grippers stack trays in precise layer patterns onto standard pallets. Slip sheets may be inserted between layers for stability. Full pallets are wrapped using a rotary arm stretch wrapper. The film roll is tensioned to apply a tight wrap without deforming the boxes. Wrapped pallets are transferred to refrigerated holding or shipping docks for distribution. Throughout the process, programmable logic controllers synchronize machine timing, belt speeds, pump volumes, and thermal settings. Human-machine interface panels monitor all parameters and log production data. The entire line is modular and scalable, allowing simultaneous production of multiple donut types. Conveyors interlink each station, minimizing manual transfer and optimizing flow. Changes in donut type or size are handled through automated tool change systems or quick swap components. Pre-programmed recipes stored in the central control system reconfigure the line settings within minutes. Staging silos and ingredient feeders are equipped with load cells to precisely meter dry ingredients. Liquid ingredients are stored in jacketed stainless steel tanks with inline agitators to prevent settling or stratification. The dry and liquid ingredient streams merge at the mixer's inlet via butterfly valves controlled by digital weigh scales. The dosing accuracy ensures batch-to-batch uniformity, critical for dough performance during proofing and frying. Proofing chambers are equipped with belt elevation systems that loop the dough pieces through multiple horizontal levels. Fans and humidifiers ensure even air distribution, and digital probes record temperature and humidity in real time. Fryers are segmented into temperature zones with independent heating coils managed by thermocouple feedback. This zoning ensures even coloring across all donut types, regardless of fill or topping. Oil levels are maintained by float-based control valves, and inline filtration runs continuously. Spent oil is periodically replaced using external storage tanks connected by insulated pipelines and pneumatic pumps. The icing station includes a recirculation tank and a filtration mesh that removes solid particles from reused icing. Viscosity is measured using a rotational viscometer integrated into the circulation loop. Decorative elements such as drizzle patterns or text are applied using programmable depositor heads, which trace patterns based on CAD instructions and synchronize with conveyor speed to ensure alignment. Filled donuts pass through an X-ray inspection tunnel, identifying underfilled or foreign material contaminated units. Rejected items are diverted to a side conveyor for manual review. Donuts for seasonal assortments are coded with quick response QR markers beneath their trays, allowing downstream distribution centers to sort mixed lots via machine vision systems and RFID tracking. Dunkin' Donuts. Donut production begins with dry ingredient blending, high-protein wheat flour, dextrose, sugar, soy flour, non-fat milk powder, salt, dough conditioners, and chemical leavening agents such as sodium bicarbonate and monocalcium phosphate are measured by weight and transferred into large-capacity industrial mixers using pneumatic conveying systems or gravity-fed hoppers. Liquid ingredients, including water, liquid shortening, and egg yolk solids, are preheated and pumped into the mixer via metered dosing systems. Water temperature is held between 27 to 30 degrees Celsius to activate gluten formation without overheating. Mixers equipped with high-torque planetary paddles operate in timed cycles to combine the dough, typically lasting 8 to 12 minutes. Dough temperature is monitored continuously with inline probes. Target final dough temperature is around 27 degrees Celsius for yeast-raised donuts to ensure optimal proofing behavior. Once mixed, the dough is transferred to a resting trough conveyor for gluten relaxation and hydration equilibrium, allowing for consistent sheeting performance. The rested dough moves to a multi-stage sheeting system composed of compression rollers that gradually reduce thickness in incremental stages. Roller gap adjustments are motorized and recipe controlled. Final sheet thickness is typically 9-11 mm, depending on the donut style. A light dusting system applies fine cornstarch or rice flour across the dough sheet surface to prevent sticking. The sheet then feeds into a rotary die cutter system. The cutter contains interchangeable dies for different donut varieties, including ring shapes, filled rounds, bars, and novelty shapes. The cutting drum rotates in synchronization with the conveyor to ensure clean, high-speed cuts. Cut donuts are transferred onto wire mesh proofing trays by vacuum-assisted pick-and-place systems. The trays are automatically stacked into a multi-tiered conveyor rack that moves through a temperature and humidity-controlled proofing chamber. Proofing conditions are held at 38 to 40 degrees Celsius, with 80-85% relative humidity for 35 and 45 minutes. Within the proofer, dough pieces rise and expand due to yeast activity. Conveyor motion is timed so that each tray spends the same duration in the chamber. Sensors track fermentation progression using size and weight benchmarks. After proofing, trays enter an automated unloading system that transfers the dough pieces onto a fryer in-feed belt. Frying oil is a refined, high-stability vegetable shortening maintained at 185 or 190 degrees C. The fryer contains a dual-zone heating configuration and a submersion system using paddle arms that guide and flip the donuts midway through frying. Total fry time is approximately 90 seconds. Ring donuts are flipped automatically after 45 seconds by rotating bars. Filled donut bases remain face up to maintain a flat bottom. Oil turnover is managed through continuous filtration using a centrifugal separation system and micron-level mechanical filters to remove particulates. As the donuts exit the fryer, excess oil is removed by angled mesh belts and compressed air nozzles. Products then travel along a cooling conveyor system with ambient airflow, reducing surface temperature below 35 degrees C before handling. Ring donuts destined for glazing pass under a waterfall-style glazing station. The glazing tank contains a high-shear mixer that maintains solution homogeneity. A recirculating pump delivers glaze to a curtain nozzle that flows over the donuts. Excess glaze drains back into the holding tank through a mesh screen. Filled donuts proceed to a pressurized injection system. Each donut aligns with a dual or quad nozzle filler head that penetrates the side or bottom. Piston pumps dispense fillings such as jelly, cream, or custard with precision-controlled volume, typically 18 to 25 grams per unit. After filling, donuts requiring icing are transferred to a top-down depositor. This system uses heated reservoirs that keep icings at 40 to 45 degrees Celsius. Servo-controlled valves open and close based on donut presence detected by photoelectric sensors. Depositor heads apply a measured layer of icing across the top surface. For varieties requiring toppings, donuts travel under a vibratory topping applicator. Toppings such as chopped peanuts, sprinkles, or coconut shavings are dispensed via a rotating auger or oscillating tray, which evenly distributes material across the icing surface. Adhesion is achieved by timing the topping deposit immediately after icing application. Powder-coated or sugar-rolled donuts are conveyed into a rotating tumbler drum. A controlled feed of granulated or powdered sugar enters through a dosing hopper. The drum rotates at a calibrated RPM to coat donuts uniformly without damaging their structure. Fine mesh filters remove sugar clumps from the recirculation stream. Donuts with drizzle designs undergo a separate decoration process using linear motion gantry arms. These arms carry nozzles that deposit thin lines of icing, chocolate, or flavored syrup in programmed patterns. Motion control algorithms synchronize nozzle movement with conveyor speed for accurate designs. Post-decoration, all donuts pass through a spiral cooling tower. This vertically stacked conveyor system allows compact, high-capacity cooling with continuous airflow. Residence time is typically 15 to 20 minutes, allowing toppings to set and fillings to stabilize. Donuts exit the spiral cooler and enter a high-speed vision inspection system. Industrial cameras mounted above and to the side scan each product. Parameters such as size, color, symmetry, icing coverage, and fill injection marks are analyzed in real time. Out-of-spec items are removed via air-jet ejection systems. Acceptable donuts are organized into lanes using servo-driven diverter arms. Grouping is based on variety and pack size. Collation belts accumulate donuts into patterns that match tray cavities. Packaging begins with automatic tray erecting. Flat paperboard blanks are fed into a forming unit that applies glue and folds trays into shape. Form trays move beneath pick-and-place units with vacuum suction cups that deposit donuts into each cavity. Assorted variety packs are assembled by robotic gantries with product recognition software. These systems pull donuts from buffer conveyors and place them according to pre-programmed variety maps. Tray sealing depends on the product format. Some are closed with plastic lids, applied and snapped into place by mechanical presses. Others use film sealing units with heated jaws that apply plastic film over the tray and bond it along the edges. Package trays are labeled using thermal inkjet printers. Labels include production codes, variety, and timing information. Alignment sensors ensure accurate label placement without interrupting conveyor flow. Trays are loaded into cardboard master cases using side loading systems. Collapsible cases are automatically erected from flat blanks and fed into the loading station. Case flaps are glued and sealed using hot melt adhesive heads. Filled master cases are conveyed to a robotic palletizer. A vision-guided robot stacks cases in alternating patterns for load stability. Slip sheets are added at programmed intervals to separate layers. The stack height is optimized for transport requirements. Each completed pallet is wrapped with stretch film using a rotary arm wrapper. The arm spins around the stationary pallet, tensioning the film for secure transport. Film overlap and wrap count are controlled digitally to match load size. Wrapped pallets are labeled with barcoded identification tags applied by robotic labelers. Pallets then enter a gravity-fed conveyor line toward refrigerated loading docks or cold storage. Throughout the production line, operations are governed by a distributed control system. Programmable logic controllers handle station-level automation, while supervisory control and data acquisition systems log all machine parameters, production metrics, and alarms. Recipe management software controls all batch-dependent variables, including mixing time, proofing duration, fryer temperature, fill weights, and topping dosages. Each donut type has a profile stored in the system, allowing for rapid product changeovers with minimal downtime. Dry ingredient silos are equipped with level sensors and load cells. Refilling is coordinated with automated delivery systems to ensure continuous availability. Ingredient dosing systems operate under gravimetric and volumetric control for precise formulation. Liquid shortening is held in insulated tanks with inline heaters and agitators to maintain uniform viscosity. Delivery lines are jacketed and circulate hot water to prevent solidification. Pumps use variable frequency drives to adjust flow rate based on batch requirements. Filling hoppers for creams and jellies are jacketed for temperature control and agitated to prevent phase separation. Fill viscosities are monitored using inline viscometers, and pressure is regulated to prevent overfill or underfill. Proofing conveyor belts are made from non-stick, food-grade materials and guided on multiple horizontal tiers. Air circulation is forced through dampers to ensure uniform proofing across all trays. Temperature and humidity are logged for each cycle. Fryer systems include zoned heating elements and oil curtain barriers to minimize heat loss. Oil flow rate and turnover frequency are tracked by volumetric flow meters and recirculation pumps. Air knives at the fryer exit are powered by centrifugal blowers with adjustable nozzles. Their position and pressure are calibrated to strip excess oil without disturbing surface structure or toppings. Glazing tanks are cleaned and refilled on a timed schedule using CIP circuits. Glaze viscosity is maintained with real-time temperature feedback loops and monitored by rotational viscometers. All conveyors, transfer points, and topping stations are modular and mounted on quick-release brackets, allowing reconfiguration for new product lines or seasonal variations. The manufacturing process for Chips Ahoy! Cookies begins with precise dry ingredient batching. Key components include enriched wheat flour, sugar, brown sugar, baking soda, salt, and emulsifiers. These dry ingredients are stored in silos or super sacks and automatically dispensed via auger-fed feeders into high-capacity weigh hoppers. Load cells measure each ingredient to exact tolerances before being discharged into the mixing system. In parallel, liquid ingredients are prepared. These include water, high fructose corn syrup, molasses, glycerin, and vanilla flavoring. Liquid fats such as palm or soybean oil are stored in heated, jacketed tanks and pumped through insulated lines to maintain target viscosity. Liquid dosing is controlled using flow meters and metered pumps integrated into the batch control system. All ingredients are conveyed to an automated horizontal batch mixer. The mixing cycle follows a strict sequence: creaming of fats and sugars first, followed by the introduction of liquid components, then gradual incorporation of dry flour-based ingredients. Mixing speed and time are controlled by PLCs based on the dough formulation. Dough temperature is maintained between 20 or 34 degrees to preserve texture consistency. Once the base dough is formed, chocolate chips are added. These are stored in climate-controlled hoppers to prevent melting or clumping and are added during the final low-speed mixing phase to avoid breakage. Chip loading is calibrated by weight to ensure uniform distribution across the batch. Mixed dough is discharged from the horizontal mixer into a dough handling system, which typically includes a feed conveyor and a rotary chunker. The chunker breaks large volumes into manageable portions for downstream processing. Dough portions are conveyed to the forming line. Portioned dough enters an extrusion-based depositor system. The depositor uses servo-controlled pistons to extrude dough through circular nozzles onto a moving oven band. Each cookie unit is dropped at exact intervals to maintain spacing and size. Depositor nozzles are non-stick coated and fitted with sensors to detect flow irregularities. The formed dough pieces move directly into a multi-zone continuous baking oven. The oven band is typically a steel mesh or solid band, depending on desired bottom texture. The oven is divided into several independently controlled thermal zones, with temperatures ranging from 180 degrees C to 230 degrees C. Baking duration is precisely set, typically between 6 to 10 minutes. As cookies move through the oven, moisture evaporates rapidly in the early zones, setting the outer structure. Later zones apply radiant and convection heat to develop interior texture and caramelization. Infrared sensors monitor surface temperature, and humidity sensors measure exhaust moisture for quality tracking. Exiting the oven, cookies pass onto a series of wire mesh cooling conveyors arranged in serpentine or spiral layouts. Ambient forced air circulates across multiple tiers to reduce cookie temperature from above 112 degrees to below 35 degrees within 8 to 12 minutes. Cooling speed is critical to avoid cracking or warping. Cooled cookies then enter a vision inspection system. High-speed cameras and image processing software detect dimensional conformity, color uniformity, chip distribution, and surface defects. Defective units are ejected via pneumatic actuators or diverter arms. Passing inspection, cookies are aligned into lanes via vibratory feeders and belt diverters. Lane alignment facilitates entry into the packaging system. Product counters track units per minute and signal robotic collators when batch quantities are ready. Packaging begins with slug loading. Cookies are grouped into vertical stacks, or horizontal slugs using indexing belts and pushers. Slug formation is synchronized with wrapper film feed using registration marks and encoder-driven rollers. Each cookie slug is pushed into a horizontal flow wrapper. Wrapping film is heat sealable and typically polypropylene based with a moisture barrier coating. The film unwinds from a roll and wraps around the cookie slug as it is propelled forward. Longitudinal and transverse heat sealers create the fin seal and end seals in rapid succession. Sealed packs exit the flow wrapper and pass under an inkjet coder that prints date codes and batch identification using edible grade ink. The print head operates in coordination with conveyor speed to maintain legibility. Wrapped packs are conveyed to cartoning machines. Here, cartons are formed from flat blanks by mechanical arms and glue stations. Wrapped slugs are side-loaded into open cartons, which are then closed, sealed, and printed with product and batch information. Cartons are grouped into shipping trays using automated case packers. These machines use robotic pick-and-place arms or pusher mechanisms to load cartons into corrugated cases. The case flaps are sealed using hot melt glue or tape applicators. Full cases move to a robotic palletizer station. Cases are arranged into a predetermined pallet pattern, layer by layer. Slip sheets may be added automatically between layers to improve load stability. Each layer is compressed slightly to ensure uniform height. Completed pallets are conveyed to a stretch wrapping station. A rotating arm or turntable applies plastic film under tension, with pre-stretch rollers ensuring optimal film usage and secure load containment. Wrapping cycles are adjusted for pallet height and weight. Each pallet receives a scannable barcode label printed by an industrial thermal printer. Labels are applied on two adjacent sides for redundancy. Pallet data is logged into the central warehouse system for tracking and inventory. Control. Ingredient replenishment is coordinated with automated inventory management. Raw material silos and liquid tanks are equipped with level sensors and integrated into the batch scheduling system. Ingredient usage is monitored in real time to prevent production interruptions. Throughout the production line, all mechanical systems are controlled by PLCs communicating through an industrial Ethernet network. Recipe parameters are stored in a central HMI interface, allowing operators to switch product types by loading preset programs. Mixing cycle parameters include motor torque, bowl rotation speed, and batch temperature. If values deviate from preset ranges, alarms are triggered, and production can be halted for correction. Chocolate chips are dispensed through vibratory feeders equipped with mass flow sensors. Feed rate is adjusted automatically to match dough throughput. Chips are gently folded into the dough using planetary paddles to preserve shape and prevent smearing. Extrusion depositors are cleaned and recalibrated between batches. Nozzle calibration uses laser measurement systems to verify uniform drop size across all channels. The baking oven includes thermal profiling tools, traveling temperature probes mounted on dummy cookies that measure time and temperature exposure across zones. These profiles are compared to standard references to ensure bake uniformity. Airflow in the cooling conveyor is managed by adjustable baffles and high-volume blowers. Zones are configured to prevent condensation or localized overheating, which could impact texture. Packaging film is spliced automatically using a festoon buffer system, allowing roll changes without stopping the wrapper. Splice detection sensors verify successful transfer and trigger rejection of the transition pack if required. Flow wrappers are equipped with film tracking systems using edge guide sensors to maintain alignment. Tension controllers manage unwind force to prevent film distortion. Cartoning machines feature vision systems that verify correct pack orientation before loading. Misoriented or missing packs trigger reject mechanisms that divert affected cartons to inspection lanes. Case packers use Delta-style robots with suction grippers or mechanical claws. Gripping pressure is adjustable to avoid crushing while maintaining speed. Robot arms operate on articulated joints with sub-millimeter precision. Palletizer systems incorporate automatic pallet dispensers and slip sheet feeders. Gripper heads are interchangeable for different case sizes and stacking formats. Production data, including line speed, output volume, defect rate, and downtime, is continuously recorded and transmitted to a manufacturing execution system. Reports are generated hourly for supervisory review and performance tracking. Temperature-sensitive ingredients, such as chocolate chips and syrup, are stored in climate-controlled zones. Delivery lines use nitrogen flushing or vacuum seals to prevent oxidation and contamination. Finished goods are staged in a climate-regulated buffer zone before loading. Inventory movement is tracked via RFID-tagged pallets, which interface with the logistics management software. Cheetos are produced using a high-output, continuous extrusion system designed for the transformation of dry cornmeal into expanded puffed snacks through controlled heat, pressure, moisture, and mechanical shear. The raw material input begins with degermed cornmeal, which is stored in silos, connected directly to the process line through a network of pneumatic conveyors. The cornmeal is sifted through mesh screens to remove foreign particles, then passed through a dehumidifying chamber to achieve a standardized moisture content between 10.5 and 11.5% before entering the preconditioner. In the preconditioning chamber, dry cornmeal is mixed with water and steam under tightly regulated parameters. The purpose of preconditioning is to hydrate the meal to a target range of 18 to 20% moisture, while partially gelatinizing the starch to prepare it for the extrusion stage. The chamber uses dual shaft paddles rotating at independent speeds to ensure homogeneous hydration without introducing air pockets. Live steam is injected directly through precision steam valves with real-time moisture levels monitored using NIR, near-infrared, sensors, and inline conductivity probes. From the preconditioner, the moistened meal is transferred directly into the barrel of the extruder. The extruder is a twin screw or single screw configuration depending on the specific formulation, with segmented barrels for independent control of heating zones. Each zone of the extruder barrel is jacketed and fitted with thermocouples and pressure sensors. The screws inside the extruder rotate at speeds between 300 and 600 RPM and apply intense shear, mixing, and compression to the meal. As the material travels along the screw channel, the combination of mechanical energy and barrel heating increases the temperature of the dough to 140 180 degrees, while the pressure rises to 1500 to 3000 psi. Under these conditions, the starch within the cornmeal fully gelatinizes and the protein matrix denatures, forming a viscous melt that is cohesive and plastic in behavior. At the final die plate, the pressurized melt exits into atmospheric pressure, causing rapid vaporization of internal moisture. This sudden expansion creates the puffed structure of the Cheeto. The die shape is critical for the form factor of the snack. For classic crunchy Cheetos, the die orifice is a small circular hole, and the dough extrudes as a continuous rope. A rotating knife positioned at the exit face of the die cuts the rope into short, irregular lengths at 200 and 400 cuts per minute, depending on the desired texture. The extruded pieces fall onto a vibrating conveyor belt that transports them into the frying system. For crunchy variants, the base extrudates are fried in a continuous oil bath system. The fryer is filled with vegetable oil, commonly corn or canola oil, maintained at 170 to 190 degrees Celsius, using heat exchangers and recirculation pumps. The extrudates enter on a submerged conveyor belt that keeps them fully immersed for 30 to 45 seconds. During this time, surface water evaporates, and the structure is locked in through rapid dehydration. Oil absorption is measured using inline sensors and confirmed by batch gravimetric analysis. After frying, the product is lifted out of the oil and passes through a cascade of air knives or centrifugal de-oiling drums to remove excess surface oil. The fried product is then conveyed through a multi-stage cooling tunnel where ambient or chilled air flows across vibrating trays to reduce product temperature to under 40 degrees Celsius before seasoning. Airflow is adjusted with dampers to maintain a uniform cooling gradient and avoid moisture migration. For puffed variants, the extrusion process differs at the post-extrusion stage. Instead of frying, the puffed extrudates are conveyed directly into a hot air dryer. The dryer operates at 120 to 160 degrees and includes multiple conveyor decks with perforated trays. Heated air is circulated through the product bed at controlled velocities and relative humidity. Residence time in the dryer ranges from 8 to 12 minutes, depending on piece size and moisture content at exit. Final moisture is targeted at 2 to 3% by weight. After drying or frying, Cheetos pieces are conveyed to the seasoning drum. This is a rotating cylindrical tumbler lined with helical flights to elevate and tumble the product uniformly. The base seasoning is stored in a hopper above the drum and dispensed through a vibratory feeder into a powder application system. Oil-based or water-based slurries are sprayed through atomizing nozzles onto the surface of the snacks as they rotate inside the drum. The seasoning adheres to the surface oil or residual moisture, forming a uniform coating. The slurry composition includes cheese powder, salt, flavor enhancers, colorants, and anti-caking agents. Slurry viscosity is controlled through inline viscometers, and pump speed is adjusted accordingly. Spray coverage is monitored using camera-based imaging systems that detect color uniformity across product samples. Seasoning overuse or underuse is automatically corrected by adjusting feeder rates or nozzle flow. Seasoned snacks are passed through a final cooling stage to ensure surface dryness and coating fixation. Cooled air is circulated over a vibratory conveyor bed, and product temperature is lowered to under 30 degrees. The flow rate and cooling length are calibrated to prevent clumping in the packaging stage. Once cooled, the product is conveyed to the weighing and bagging station. Multi-head combination weighers are used to portion the product into precise fill weights, typically between 15 and 300 grams, depending on bag size. Each head drops a known quantity into a central chute when the calculated sum matches the target fill weight. The portioned product is dispensed into pre-formed bags or into a form-fill-seal machine. The vertical form-fill-seal system uses film rolls printed with product branding. The film is fed through a forming collar, sealed longitudinally, and then sealed at the top and bottom to create a pillow pouch. The filled bags pass through a check weigher and metal detector. Packages outside the weight tolerance or those triggering metal detection are automatically ejected via pneumatic arms. Conforming bags are grouped and conveyed to case packing robots. Robotic arms, equipped with vacuum grippers or mechanical paddles, load bags into pre-erected cartons or display-ready trays. Cartons are closed using hot melt adhesive and labeled with product code, batch number, and expiration date, using print and apply labelers. Finished cartons are then conveyed to the palletizer. Palletizing robots stack cartons onto wooden or plastic pallets according to a programmed pattern. Each layer is compressed to improve load stability, and the full pallet is stretch wrapped using a rotary arm wrapper. The pallet is labeled with an SSCC code and barcode linked to the manufacturing execution system. Pallets are transferred to the warehouse and stored under controlled humidity and temperature until distribution. Throughout the process, every production parameter is monitored and logged by a centralized SCADA system. Extruder temperature, pressure, die configuration, screw speed, moisture content, oil temperature, seasoning flow, and packaging weight are all tracked in real time. Automated alerts notify operators of deviations outside process limits. Batch data is stored and used for traceability, yield calculation, and process optimization. Lay's production begins with the intake of bulk potatoes delivered by truck or conveyor into receiving hoppers. Potatoes are unloaded into flume systems filled with recirculating water, which use hydraulic movement to carry them to the first stage of processing. This flume system not only transports the potatoes, but also initiates pre-washing to remove surface soil and debris. Upon exiting the flume, the potatoes enter a rotating drum washer fitted with abrasive surfaces and high-pressure spray nozzles. This drum rotates slowly while jets of water dislodge residual dirt from the potato surface. The wash cycle time is optimized to avoid damaging the skin while ensuring that every tuber is completely clean. The cleaned potatoes are then conveyed to an inspection belt, where optical sorting systems equipped with high-resolution cameras scan for defects such as green skin, rot, or deformities. Non-conforming potatoes are removed by targeted air jets activated in milliseconds. Accepted potatoes are then directed to the peeling stage. Mechanical peelers utilize either steam pressure or abrasive rollers. In steam peeling, potatoes are exposed to high-pressure steam in a sealed vessel for a few seconds, then rapidly released into a vacuum chamber, causing the skin to rupture and loosen. The loosened skin is removed with soft brushes and water sprays. In abrasive peeling, the tubers are rotated inside a drum lined with abrasive surfaces that scrape the skin off while minimizing flesh loss. After peeling, potatoes are rinsed again to remove any residual skin particles. Peeled potatoes are conveyed via stainless steel belts to slicing machines. These are centrifugal slicers equipped with rotating impellers that force each potato against razor-sharp blades mounted on a rotating head. Blade thickness is adjustable down to tenths of a millimeter to produce slices typically between 1.2 and 1.5 millimeter thick. The speed of both the impeller and cutting head is synchronized to maintain consistent thickness regardless of potato size. Slices exit the cutter in a continuous stream and are immediately passed through a water flume to prevent browning caused by enzymatic oxidation. The sliced potatoes are then subjected to blanching. This step involves immersion in hot water or passage through a hot water curtain at 65 to 75 degrees Celsius for 1 to 2 minutes. Blanching reduces starch levels on the surface of the slices, which is necessary for achieving uniform golden color and reducing sugar-related dark spots during frying. It also partially gelatinizes surface starch, which influences final texture. After blanching, the slices are rinsed with cold water and passed over dewatering screens or air knives that remove excess moisture before frying. Next, the slices enter the continuous frying system. The fryer consists of a stainless steel trough filled with vegetable oil, maintained at a temperature between 170 and 190 degrees Celsius, using external heat exchangers and recirculating pumps. The oil is filtered continuously using inline centrifugal or bag filtration systems to remove fines and prevent degradation. Slices are carried through the fryer on a submersion belt that ensures each one is fully immersed for a specific dwell time, usually between 2 and 3 minutes. The exact time and temperature profile is controlled by SCADA systems to produce chips with consistent moisture content below 2%. As the chips exit the fryer, they pass through an oil removal system consisting of vibrating conveyors and high-velocity air blowers or centrifugal de-oiling drums. These reduce surface oil, improving shelf life and texture consistency. The chips are immediately cooled by ambient or chilled air using tunnel coolers that bring the product temperature down below 40 degrees Celsius within 90 seconds. This cooling step also halts cooking and stabilizes texture. After cooling, the chips enter the seasoning system. A vibratory conveyor feeds them into a rotating drum lined with helical flights to provide continuous tumbling. Liquid or powder seasoning is applied via spray bars or auger-fed dosing units mounted above the drum. Liquid flavor systems use oil-based carriers with atomizing nozzles to create fine, even coverage. Powder seasonings are dosed based on real-time weight feedback to maintain precise seasoning ratios. The tumbling action ensures uniform adhesion of the seasoning to the chip surface. From the seasoning drum, chips are transferred via vibrating or belt conveyors to the packaging area. Along the way, they pass through optical inspection systems that detect burnt or misshaped chips using near-infrared cameras and remove them using targeted compressed air pulses. Chips then fall into the radial combination weigher, which consists of multiple buckets that each dispense a known quantity. A computer selects the optimal combination of buckets to match the target fill weight with high accuracy, typically within plus 0.1 grams. Portioned chips are released into the forming tube of a vertical form fill seal machine. Here, pre-printed film is formed into a tube sealed longitudinally and sealed at the bottom to form a pouch. The chips are dropped in, and the top is sealed to complete the package. The seal jaws also cut the film to separate each bag. Each package passes through a check weigher to verify total mass and a metal detector to ensure food safety. Out-of-spec packages are automatically ejected onto a rejection lane. Accepted packages move to high-speed collation and case packing systems. Multiple bags are grouped together using timing belts and dropped into pre-formed cartons or display trays. Automated case sealers close and glue the boxes. A print and apply labeler affixes tracking labels with batch number, expiration date, and barcode. Cartons are conveyed to a robotic palletizer that stacks them according to pre-programmed pallet patterns, optimizing space and transport efficiency. Full pallets are wrapped in stretch film using a rotary arm or turntable wrapper. A barcode, label with product and pallet ID is applied. Pallets are transferred to a climate-controlled warehouse held at consistent temperature and humidity to preserve texture and prevent oil oxidation. All product data, including ingredient lot numbers, frying oil batch, line performance data, and packaging codes are stored in the plant's MES database for full traceability. Throughout the process, ingredient inputs, machine speeds, temperatures, moisture levels, oil quality, and product weights are monitored in real time by integrated control systems. Operators interface with the process through HMI panels, which display alarms, trends, and machine statuses. Recipes are stored digitally and selected at line start to automatically load all relevant parameters across slicing, frying, seasoning, and packaging modules. Cleaning between flavor changeovers involves flushing, slicing, and seasoning systems, draining and filtering oil as needed, and changing packaging film rolls. Flavor specific. Residue is minimized through modular drum systems that can be swapped out quickly and cleaned offline. Line efficiency and waste percentages are recorded for each run and reviewed during shift changeover meetings for continuous improvement. A high-capacity Lay's line is capable of producing between 10 and 15 tons of finished chips per hour, depending on chip type, size, and flavor. Lines can operate for up to 20 hours per day with planned cleaning and maintenance windows. Raw potato usage, slicing yield, oil usage, seasoning consumption, and finished product throughput are tracked and analyzed daily for operational optimization. Doritos are produced using a continuous process that begins with raw corn as the base input. The corn arrives in bulk and is stored in vertical silos with aeration systems to maintain stable moisture content. Each batch is gravity-fed into a cleaning system where the kernels pass through vibrating screens, destiners, and aspiration channels to remove dust, stones, and foreign matter. Magnet separators extract any ferrous contaminants before the corn enters the next stage. The cleaned corn is fed into a steeping tank or continuous cooker where it is exposed to water at temperatures between 80 and 100 °C. The corn remains in this system for 30 to 45 minutes, depending on its initial hardness and desired hydration level. Water is continuously circulated and filtered to remove loosened pericarp, and the corn's internal moisture content rises to around 40 to 45%. Cooked corn is discharged onto dewatering screens and conveyed to the stone mill. The stone mill grinds the wet corn into masa, a soft, pliable dough. The grinding mechanism consists of two rotating stones, one fixed and one rotating, with adjustable spacing to control grind texture. The heat and friction from grinding partially gelatinize the starch. The resulting masa is collected in a trough and transported via auger to the sheeting system. No preservatives or additives are introduced at this stage. Masa is fed into a sheeter system consisting of dual rollers, calibrated to produce a uniform sheet of dough at a thickness between 1.2 and 1.5 millimeters. The sheet is continuously monitored using laser micrometers that provide real-time feedback to the roller gap actuators. The dough sheet moves onto a die-cutting system where rotary cutters stamp out the triangle shape of each Dorito. Scrap masa is collected and returned to the auger to be reblended into fresh dough within a defined recycle ratio. Cut chips move on a perforated conveyor where they are lightly dusted with corn flour to prevent sticking, and then enter a 3-zone oven. The oven zones are independently controlled for temperature and airflow. The chips are partially baked at 300 to 400 cuars de croix over a total residence time of 45 to 60 seconds. This reduces surface moisture and creates a semi-rigid structure suitable for frying. The internal moisture content is reduced to around 20% by weight. Partially baked chips exit the oven and are transferred via vibratory conveyors to the continuous fryer. The fryer is filled with high oleic vegetable oil, typically corn or sunflower oil, filtered and recirculated through plate filters to maintain clarity and reduce polar compound formation. Oil temperature is held at 180 to 190 degrees Celsius. Chips enter on a submersion belt and are fried for 50 to 90 seconds, depending on their moisture content and thickness. During frying, final moisture is reduced to less than 2%, and texture is developed through rapid dehydration and surface expansion. Upon exiting the fryer, the chips pass through an oil removal stage. This includes air knives and optionally a centrifugal de-oiling system that rotates baskets at up to 1000 RPM to spin off residual oil. After de-oiling, the chips enter a cooling conveyor system where ambient or chilled air flows across a vibrating bed to bring product temperature below 40 degrees Celsius in under 2 minutes. The cooled chips are then routed into the seasoning drum. This is a horizontal, cylindrical tumbler fitted with internal flights that lift and rotate the chips as they pass through. Seasoning application occurs via 2 systems: dry powder feeders and liquid slurry sprayers. The dry powder feeder consists of a vibratory tray with variable speed auger dispensing seasoning mix at a calibrated rate. Liquid slurries containing oil-based flavor carriers are sprayed using pressure nozzles fed by gear pumps. Flow rates are adjusted in real time based on chip throughput measured by load cells at the drum's infeed. Seasoning distribution is monitored using optical cameras and hyperspectral imaging to evaluate surface coverage and color uniformity. If discrepancies are detected, feed rates are adjusted automatically. Once seasoned, the chips are conveyed to the packaging section. En route, they pass through inspection systems that identify and reject burnt or broken chips using high-speed cameras and targeted air jets. The accepted chips are transferred to multi-head combination weighers. These weighers consist of multiple hoppers, each holding a portion of chips. A computer algorithm selects the combination of hoppers that adds up closest to the target package weight with minimal deviation. The selected portions are released into a form, fill, seal machine. The packaging film is unwound from rolls and guided through a forming collar, where it is shaped into a tube. The back edge is sealed with a vertical heat sealer, and bottom and top seals are created by horizontal jaws synchronized with the drop of each portion of chips. Packages are filled, sealed, and separated continuously. Each bag passes through a check weigher and metal detector. Non-compliant bags are ejected automatically. Bags are transported to the collation area where they are grouped into sets for case packing. Robotic arms equipped with suction cups pick multiple bags at once and place them into preformed cartons. Cartons are closed using hot melt adhesive applied by precision nozzles and sealed under pressure. Each box is labeled with batch number, expiration date, and a scannable barcode. Cartons are transferred to palletizing cells. Industrial robots, equipped with vacuum grippers or mechanical paddles, stack cartons in a predetermined pattern onto wooden pallets. Full pallets are wrapped using stretch film applied by a rotating arm or turntable system. A final barcode is applied to each pallet for inventory tracking and scanned into the warehouse management system. Pallets are stored in climate-controlled distribution warehouses maintained at target humidity levels to prevent chip degradation. All critical production data, including ingredient batch numbers, processing parameters, oil usage, seasoning data, packaging film codes, and output weights, are logged automatically by the SCADA system. This data is linked to the finished product batch code and can be retrieved for quality control, traceability, and efficiency analysis. Flavor changes on the production line require equipment cleaning, seasoning drum swap, packaging film change, and system flush. A changeover process is executed based on preloaded digital recipes that configure roller settings, fryer dwell times, seasoning flow rates, and packaging parameters. Downtime for changeovers is minimized using quick-release parts and automated washdown stations. Production lines are modular and scalable. A high-capacity Doritos line can produce between 3 and 7 tons of finished chips per hour, depending on product format. Processing yield is calculated based on raw corn input, fryer oil usage, and seasoning weight compared to bagged product output. Efficiency metrics such as frying oil turnover rate, seasoning coverage variance, and bag fill accuracy are continuously monitored and used for process improvement. Oil management is critical in Doritos production. Fryer oil is circulated through external heat, exchangers, and filtration units that remove carbonized particles and maintain oil quality. Oil is replenished continuously and measured using inline oil meters. Oil turnover is tracked to prevent degradation, which can affect flavor, shelf life, and texture. Used oil is discharged in controlled quantities and either recycled or disposed of based on operational protocols. Seasoning systems support multiple recipe profiles. Each recipe includes component percentages, feed rates, viscosity targets for slurries, spray nozzle pressures, and pump speeds. Recipes are stored digitally and loaded via the line's control interface. Seasoning is prepared in parallel tanks to reduce downtime between batches and allow flavor sequencing. Packaging lines operate at speeds between 60 and 150 bags per minute, depending on bag size and configuration. Packaging materials are stored in automated reels with sensors that alert operators when a roll change is needed. Packaging seal integrity is tested using vacuum or burst testing at specified intervals. Seal strength and print registration are logged alongside product weight and metal detection data. Each Doritos variant, whether original, spicy, lime-flavored, or limited edition, follows the same general processing flow with adjustments made at the seasoning and packaging stages. The ability to scale and shift recipes allows the production line to handle dozens of flavor profiles without hardware changes beyond seasoning and film adjustments.